This is part 3 of the series, The Basics of Geometry. In the last part, we introduced the idea of postulates. And the first postulate that we're going to be working with is known as the ruler postulate. The ruler postulate is a fairly simple one. It has two basic parts. The first part says that points on a number line can be paired with real numbers called coordinates. So here we have a number line. We have point K and point J, and we paired those with the numbers -2 and 5. The second part of the postulate says the distance between the 2 points on a number line is the absolute value of the difference of the coordinates. So that's all you have to do is take the first one, -2, subtract the second one from it. -2 minus 5 is -7. Take the absolute value of it, and that's 7. So here we can see from -2 to 0 there's 2 units, and from 0 to 5 there's 5 units, which is 7 total. So this gives us a really quick and easy way to find the length of any straight segment. Now we're going to have to do something different when we're in a coordinate plane and we have diagonal lines or lines that are not either straight across or up and down. But whenever we have something on a number line that's straight across, or if it's a vertical number line, it's very easy to just employ this ruler postulate. So again, the distance between any 2 points on a number line is the absolute value of their difference. The second postulate that we're going to be working with also deals with segments, but this one has a couple of more pieces. So let's take a look at that next postulate. This postulate is called the segment addition postulate. And it's the idea of betweenness. That is, it talks about point B being between A and C because the length of AB plus the length of BC is equal to the length of AC. So just to try and make this a little bit clearer, let's use some numbers. Let's put a 3 here. So the length of AB we'll call 3 units, and the length of BC we'll call 5 units. Well, you can clearly see that AB plus BC, so the length of AB, which is 3, plus the length of BC, which is 5, equals this thing tacked onto the end of this thing equals this whole thing from here to here, which is going to be equal to AC, which equals 8. Now, if I tried to convince you that point C was between A and B, then that would mean that AC plus BC would have to equal AB. Well, you can clearly see that since AC is 8 and BC is 5, that AB is definitely not going to be 13. So, at least not in this universe anyway, 13 cannot equal 3. So this is the idea of the segment addition postulate. Think of it in even simpler terms. The two smaller objects added together make up the big one. So the small one AB plus the big one BC equals the bigger one AC. Very simple. So just to make sure that we got the idea down, let's work a quick example. Here we're given that segment LN is 42 units long. LM is 12 units. We want to find MN. So using the segment addition postulate, we know that LM, the length of LM, plus the length of MN equals the length of LN. Putting in our values, LM is 12, plus MN is our variable, equals LN, which is 42. We subtract 12 from each side, MN equals 30. So that's the segment addition postulate. Let's move on to the next idea. In this case, we're going to be going to a coordinate plane that's going to be looking at segments in 2 dimensions now. instead of just one, either straight across or up and down. Here we have a coordinate plane. This is also known as a Cartesian plane, Cartesian coordinates. You may recall that from your algebra days. This plane has 2 points, point P and point Q. The coordinates of point P is x1, y1. This ordered pair is always x first, y second. Q is x2, y2, so your x and y. Now, to find the length of this segment, what we're going to do is we're going to use an offshoot of the Pythagorean theorem. Now, you may recall the Pythagorean theorem. You may be thinking to yourself, you're probably thinking to yourself, a squared plus b squared equals c squared. That's not the Pythagorean theorem. The Pythagorean theorem says the sum of the squares of the legs of a right triangle equals the square of the hypotenuse. So if we wanted to label this A and this B and this C, then we could use the formula a squared plus b squared equals c squared as a representation of the Pythagorean theorem, but it is not in and of itself the Pythagorean theorem. So that's what we're going to do. I'm going to go ahead and label this leg A, this leg as B, and the hypotenuse as C. And we'll go ahead and write our wonderful little expression here. We'll say c squared equals a squared plus b squared. So the sum of the squares of the legs equals the square of the hypotenuse. Now if we take a look at the length of this leg, using the ruler postulate, we know that the length of this segment is the absolute value of the difference of its coordinates. Well, the coordinates of this segment, since this is going straight across, is simply x1 and x2. So we take the difference, x2 minus x1. That gives us the length of this segment. So the absolute value of x2 minus x1 is the length of A. So the absolute value of x2 minus x1 gives us our A value, and we're going to actually square that value. Plus, the same thing could be true of this. The coordinates of this point, we're looking for the vertical coordinates, which are the y's. So y2 minus y1 using the ruler postulate, that gives us the length of this segment. So this would be the absolute value of y2 minus y1. And we're going to square that, and that equals this hypotenuse squared, c squared. Well, this c is simply the distance between P and Q, so we can either call it distance or we can just call it c squared. Doesn't really matter one way or another. In order to satisfy this expression, to find c, the distance, we would have to take the square root of both sides of this equation. So we take the square root of that and the square root of this. So the square root of c squared is simply c, which equals the square root of, now if we look at this value, x2 minus x1, regardless of whether this number is positive or negative, since we're squaring the value, it really doesn't make any difference whether this is positive or negative, because a negative times a negative is a positive, and a positive times a positive is also a positive. So in either case, these values, we don't really need this absolute value symbol here because we're squaring it. So it's simply x2 minus x1 squared plus the same thing here, y2 minus y1 squared. So you can see that the distance formula listed here is simply a derivation of the old Pythagorean theorem. And that's how it should be used. It's just the Pythagorean theorem. Now, we're going to work through some examples. And my recommendation is that you try working through each one of these examples on your own. And if you work through these examples and be truthful with yourself, that you can do these without looking at help after you've gotten familiar with the theorem that you should have this down and be able to work these throughout the rest of your course. Practice is key in this case. So let's continue on. Let's work a couple of examples. Now here we have PQ and the coordinates are 3, 3 and 8, 7. So using the standard distance formula, we know that the distance, we'll just call it D for short, equals the square root of the difference of the x's. So let's take our x terms. That's 3 minus 8. And again, it makes no difference if you do 8 minus 3 or 3 minus 8, because since we're squaring this value, whether this number comes out negative or positive, totally doesn't matter. Plus the difference of the y values. So it's 3 minus 7 squared. Figuring this out, 3 minus 8 is negative 5 squared, plus 3 minus 7 is negative 4 squared. Take the square root of that whole thing. That's 25 plus 16. Take the square root of that. That's the square root of 31, which is approximately equal to 5.6. Now, you may be asked to find the exact value of one of these. That would be the exact value, because 31 is a prime number. It doesn't simplify. So the square root of 31 is the exact distance between P and Q. The approximate distance is 5.6. And the reason it's approximate is because we're losing all the decimals that come after this 6 here. It's actually 5, 6, 7, 7, 6, 4, and on and on and on. So this is the approximate, this is the exact distance. Now I'm going to do this again, but this time I'm going to use a slightly different method. You might like this, you might hate this method, but I use it regularly because to me it's very, very straightforward and much quicker than going through all these gyrations. It's still the distance formula, it's just a slightly different visual form. So the first thing I do is I stack my points. So we have 8, 7, which is Q, and 3, 3. And it doesn't matter which one goes on top, which one goes on bottom. It makes no difference. And I just put a negative sign out here just to indicate that I'm subtracting. Remember, these are the x values, and these are the y values. I usually don't write this, but I'm doing this for your benefit. So 8 minus 3, 5. 7 minus 3, 4. So this is the difference of the x's, difference of the x's. This is the difference of the y's, difference of the y's. Then I just have a silly little anagram, SAS. Square, add, square root, SAS. Square, add, square root. And here you can see we have the exact same form that we have here, and obviously it results in the same final result, square root of 31. And there you go. That's the distance formula. If you like it, use it. I think this is far quicker, but it's up to you. It doesn't really matter which one you use. You can go with the formal distance formula, or you can use this idea here. In the next part, we're going to do a bunch of practice problems. So by all means, don't stop here. Go on to the next part, the next video, and work those practice problems, and you should have this down. So I will talk to you in the next part.